Hey, welcome again. Today in digital signal processing, we are going to see a new topic called as the solution of linear constant coefficient differential equation. Then what is this linear constant coefficient differential equation? Generally, any discrete systems are represented in the form of equation which tells the relation between input and output. This equation we call it as a linear constant coefficient difference equation. Generally for continuous systems we call differential equation. Discrete systems are represented using difference equation. So the general form of difference equation of nth order system, any LTI system, that is linear time invariant system, the output depends on the present input and past outputs. Thus, the equation y of n at any instant of time is given as y of n equal to minus summation k equal to 1 to capital N ak y of n minus k plus summation k equal to 0 to capital N bk x of n minus k. This equation tells that the output y of n depends on the present input. For k equal to 0, it depends on b0 x of n, that is present input. Then for k equal to 1 to capital N, that is b1 x of n minus 1, b2 x of n minus 2, like this. The output depends on the past inputs also. This y term, that is aky of n minus k, represents the past outputs. So for k equal to 1, it becomes a1y of n minus 1. For k2 equal to 2, then it becomes a2y of n minus 2. That is, output depends on the past outputs, actual outputs. So thus the equation y of n at any instant of time depends on the present input and past outputs. This type of equation we call it as a linear constant coefficient difference equation. This minus sign denotes the feedback from output to input of the past outputs. So this is a general equation where ak and bk are the constants. Now this any discrete system is represented using a difference equation. Generally, most of the discrete systems are represented using a difference equation. It can also given in the form of its impulse response, that we'll see in next video. So here we are to solve the difference equation. The general method we use to solve the difference equation is Z transform method. So here we'll use a Z transform to obtain the transfer function of a system, that is h of z equal to y of z by x of z, and we will solve this equation by using some partial fraction, and then we are finding the solution, that is y of n. Hence instead of solving the polynomial we can use the z transform. So we will solve some examples in this video. Let us go through this first example. Now what is the question? That is, solve the following second order difference equation using Z transform method, given by y of n minus 0.5 y of n minus 1 plus 0.06 y of n minus 2 equal to x of n. And the given input signal is unit step signal or unit step function, x of n equal to u of n, and the system starts with 0 initial condition, means y of minus n minus 1 y of minus 2, that is the previous outputs are 0. Now how to solve this problem? So first step we are taking the Z transform on both sides. So the Z transform of y of n represented by y of z, Z transform of y of n minus 1 will be Z inverse y of z, Z transform of y of n minus 2 will be Z to the power minus 2 y of z, and Z transform of x of n is x of z. But x of n is u of n, so you can find the Z transform of u of n. So in this I am taking the Z transform on both sides and taking y of z common. Now we are just sending the equation of x of z. We are using the equation of x of z. X of z will be 1 divided by 1 minus z inverse. This is a Z transform of unit step signal. Then substituting here. Now we are just finding y of z on left hand side and remaining on right hand side. So y of z you will get 1 divided by 1 minus z inverse and 1 minus 0.5 z inverse plus 0.06 z to the power minus 2. This is the second step. We have to obtain equation of y of z. In third step, we are going to use, first we will find the factors of denominator more if it is second order. So in the denominator we have the term 1 minus 0.5 z inverse plus 0.06 z to the power minus 2, which can further be factorized. So will get the two factors, 1 minus 0.3 z inverse, 1 minus 0.2 z inverse. So we are substituting. So this is the equation number, step number 3. Factor the characteristics polynomial. Now y of z is the equation in which it has some numerator and denominator we have factors. Now the next step we are going to use is partial fraction. This right hand side equation we are solving by partial fraction, given as a divided by first root plus b divided by second root plus c divided by third root. Then we have to obtain the values of a, b and c using the residue method. Now we already studied in previous classes how to obtain this a, b and c. So here it is given, we know. So simply to obtain value of a, we are multiplying numerator and denominator with 1 minus z inverse and set z inverse equal to 1. We got the a value as approximately 1.78. Similarly, we are finding the b value and c value. Okay, so after getting a, b and c value, we are substituting. So after substitution, what we are getting, y of z equal to 25 by 14 divided by 1 minus z inverse minus 9 by 7 divided by 1 minus 0.3 z inverse plus 1 by 2 divided by 1 minus 0.2 z inverse. So this is the step in which we are finding y of z in this form. Now to obtain the solution directly, we can take inverse z transform. So what is the next step? Applying inverse z transform. Now we know the inverse z transform in of 1 divided by 1 minus a z inverse is a to the power n u of n. So applying this formula, we can have y of n equal to 0.225 divided by 14, 1 to the power n u of n minus 9 by 7.3 to the power n u of n plus 1 by 2 into 0.2 to the power n u of n. This is a solution. Okay, so you can take u of n common or you can leave. Okay, so this will be the exact solution of linear constant coefficient difference equation. So any question asked in the same way, sometimes they may give the initial conditions, sometimes they may not give the initial conditions. In this example, we have not given any initial conditions. So this is one example. Similarly, we will solve one more example. Now see, in this example, the question is solve the following first order differential equation using Z transform given by y of n minus 0.5 y of n minus 1 equal to x of n. Here the input is step function x of n equal to u of n, and here non-zero initial conditions are given, that is y of minus 1 equal to 2. So here this is the extra thing given. Now process is same, only while finding the z transform of u of n minus k, we have to use the initial condition. So first we are applying the z transform on both sides, that is step number 1. So it will be y of z minus 0.5 z inverse y of z plus y of minus 1. So like this you have to use the initial condition, and equal to right hand side z transform will be x of z. Okay, then simply taking y of z on left hand side and x of z on right hand side. So simply rearranging the terms, we will get this. Now you can substitute x of z. As we know, x of n equal to u of n, x of z will be 1 divided by 1 minus uh, z inverse. So here not yet substituted. Okay, afterwards we'll substitute. So here simply first I am finding the equation of y of z. This term also called as a zero state response caused by input. Okay, as well as the second term represents the zero input response because it caused due to the initial conditions. Now we have to substitute x of z, which is 1 divided by 1 minus z inverse. Okay, substitution. Now this first term we have to solve. Okay, we can have cross multiplication and we have the common denominator. So solving the above equation, we are get y of z equal to 2 minus z inverse divided by 1 minus z inverse 1 minus 0.5 z inverse. Now here, as we have two roots in denominator, again you can use the partial fraction. So in step number 4, we'll apply partial fraction. We'll write a divided by first root plus b divided by second root. Again, using residue method, we are finding values of a and b, which we got 2 and 0. Simply substituting. So what we are getting, y of z you got as a y of z you got, and then we will take the inverse z. So in inverse z, we will get y of n equal to 2 1 to the power n u of n. So this is the solution of your linear constant coefficient differential equation. So this is the example number 2. And in this last example again, similarly you have to solve these questions when we ask in exam. Find the forced response of a system given by this equation. Input is 2 to the power n u of n. Now see, initial in two examples we have seen the initial, so the input is u of n, but here the input is 2 to the power n u of n, which is an exponential input and zero initial conditions. Now process is same. First step is taking the z transform on both sides, then taking y of z on left hand side, remaining thing on right hand side. We will get y of z and remaining thing on right hand side. Then substitute x of z. You know that 2 to the power n u of m z transform will be 1 minus 1 divided by 1 minus 2 z inverse. Then substitute. Then we can find the roots of this denominator. Further, we can solve for the roots of the denominator. So factor the characteristics quadratic equation. So total output we are getting y of z equal to 1 divided by first root, second root and third root. Again similarly we have to solve using partial fraction. A divided by first root plus b divided by second root plus c divided by third root. Finding the values of a, b, c. So we are getting y of z this equation. And in the same way we are taking the inverse z transform. So your output equation will be 8 by 5 to the power n minus 0.5 to the power n plus 2 by 5 0.33 to the power n into u of n. So like this we are solving. And this is one more example. You can solve in similar way. We are finding the total response. Same way, process is same. Okay, simply if initial conditions are given, use it, otherwise don't use it. So here initial condition is given, that is y of minus 1, you have to consider as a 1. Okay, so here similarly first we are finding y of z, then we are substituting x of z, and after substituting x of z, we are finding the roots of the denominator, so that we can use the partial fraction method. After applying partial fraction method, we are finding a value, b value, and the overall output you got y of z equal to minus 0.5 divided by 1 minus z inverse plus 4.5 divided by 1 minus 3 z inverse. And applying inverse z transform, the solution of the given equation will get 4.5 to the power n minus 0.5 into u of n. So like this you can solve the many examples. Here also in this example, find the total response y of n for n greater than 0 given by this equation. Input is given as a 0.3 to the power n u of n, and y of minus 1 is 5. Process is same. Okay, so simply you take care while substituting y of minus 1. So whenever y of minus 1 is given, the z transform of y of n minus 1 will be given by z inverse y of z plus y of minus n. And solve similar way, taking z transform on both sides, keeping y of z on left hand side, substituting x of z by taking z transform of input. Then see, you obtain roots of denominator. After applying the roots of denominator, we are using partial fraction, finding the values of a and b using residue method. After finding values of a and b, substitute, you will get the overall final equation of y of z. And then you take the inverse z. You will get y of n equal to this minus 0.75, 0.3 to the power n plus 5.25, 0.7 to the power n u of n. So like this you have to solve the given linear constant coefficient difference equation.